I think you are good to start. So.
Okay, thank you, Mikhail. Thank you for the opportunity to share a bit our result on this new kind of pads. We are always happy to have some feedback on what we find out or what we are, how we are discussing our results. So it is a presentation on new MRI pads made with silicon carbide for 70 MRI. It's a work that involves a lot of partners in the MCube project, and we're trying to find some kind of new prospect from the pads that are doing by Andrew Webb at Utrecht. And I will start with some kind of motivation why we would like to do a new pads. Then I will talk about a bit about the state of the art and what the group of Ulstedt have been done so far. And then I will present you the pros and cons of the pads and a few results we had when we were trying to compare our pads to the state of the art. So about the motivations, as you all know, the new trend is to get higher and higher field MRI scanner. And just because the SNR is a function of the initial field, so they are promised to deliver higher images with better spatial and or temporal resolutions. The thing is at those very high field, the wavelength is comparable to the dimension of the body part you are trying to image. At 3T, it's you will have those kind of interferences for the big organs, large organs, and at 70, most of the time it will appear in the temporal lobe in brain images. So it will result in dark areas and contrast loss. There are another way to deal with this, which is parallel transmission, but it's expensive and takes a lot of time to develop. And so in the MCube project, one of the simplest way to deal with this, and also in the literature, is to use high dielectric constant materials. With this, you will have to, it will interact with the field during the scan. And when you put this in the coil, you will have a secondary field that you can use to illuminate the dark areas. So what have been done on this? A lot of studies, of course, have been done on this the last 10 years on permittivity studies, on numerical simulations to have the optimized size or location. There is also on the right by Schmidt, someone I really love, is for some kind of permittivity pads. They are trying to change the conductivity current by make an assembly of pads. And on this one, you can see on the image B, which is we will have also for our measurement, you have a very strong field and an hole that is created. And on the image E and F, when we make an assembly of pads, they manage to get rid of the hole that is created by the pad, which is a pretty nice improvement. So far, they are working on pads that have permittivity higher than water. The first pad were made with water, of course. And because of that, you need to have permittivity range from 100 to 300. And also because of the cost and availability on the market, all the studies were mostly focused on water first, heavy water then, and after that, calcium titanate or barium titanate dispersed in heavy water. What have been seen that in the literature, there are first heterogeneity that appears over time. To illustrate that, I will show you an image where we use a pad that have been done after 6 months, and you see on the image what are the degraded brain image. And also they are rigid and massive because It's a composite by nature, so you have to pour a lot of particles inside the solvent. And as you know, the space in the coil is very limited. So you will end up with something most of the time big and uncomfortable for the patient. So we were trying to, go beyond that. And we aimed at something that is harmless, inalterable, and also that may increase field at least at as good as the perovskite pads. First, for the inalterable side, we work on a very particular solvent. It is a solvent that has the same permittivity as water, which is very important because it will be the matrix of the composite. And also, the fusion temperature is slightly above 25 degrees. It means that when we use it, it has a very pasty texture. And with that kind of texture, the solvent is less prone to evaporation. And added to the fact that the boiling temperature is twice higher than heavy water, you will have something that could last for more than 6 months. Actually, I've made permittivity measurement on the same pad for 1 year, and I always had over 1 year the same permittivity levels. After that, we added silicon carbide particles. Why? Mostly because barium titanite is something that is harmful, and we were trying to find something with high permittivity, which you use in everyday life. For example, when you go fishing, I forgot the word. The equipment you use to fish when you go fishing is made with silicon carbide, and there are a lot of material that is very hard made on with silicon carbide. And also by using something that is much less harmful than barium titanate, we aim at easier the translation to everyday use and clinical routine by a faster CE mark process. And finally, we added a dispersant. The group of Andrew Webb also added dispersant with in their paper, but we really needed that to have a homogeneous composite. So we aimed at something that does not lose properties over time, that is pasty, so comfortable and less prone to evaporation, and something that is much safer. After that, we were looking for something with the same performance level as the perovskite, and in those pads, performance level is mostly driven by low permittivity, high permittivity, but low conductivity. In our case, on the left side, you can see the volume content of dielectric material as a function of a real part of permittivity for barium titanate in heavy water and silicon carbide in polyethylene glycol. As you can see, they have the same permittivity level. But on the right side, you have the conductivity as a function of volume content of dielectric material. We have much higher conductivity because mostly of the the slurry agent we added. So we end up with something with the same performance power of perovskite, but maybe with higher conductivity, we could expect drop of performance on one side and also higher SAR levels on the other side. So we were trying to assess those performance through both measurement on SAM and on volunteers. And here first I will show you the SAR measurement on CST on Gustav by using a coil that resonates as the same frequency as a 770 scanner. And what you can see on the right are the subsection of Gustav with and without pad located on the ear. And for the pad, we used the most common pad in literatures. So 10 by 10 for barium titanate and silicon carbide, and calcium titanate 18 by 18. So the barium titanate and silicon carbide are roughly the same permittivity level, but calcium titanate has a permittivity level of only 100. And for local SAR, we computed value for the subtraction of the highest value of SAR, which is not always on the same point. And for global SAR is the mean value of SAR. And as you can see, for barium titanate and silicon carbide, the local SAR variation and global SAR variation are the same order of magnitude. And for calcium titanate, which is mostly due to the fact that they are very, very large, you have a local CAR increase of more than 10% on both cases. I must add that for us, it validates the use of those material as safe, because most of the pads sold by Andrew Yeb and also by my company now are made of calcium titanate. So far, of course, the SAR are a bit higher than the two others, but they are the pads that are the most used, on at least in laboratories. After that, we continued those, we wanted to compare those assumptions with B1 plus maps on SAM at 70 at neurospin, and then on volunteers, following a protocol that was described in a paper by Alexandre Vigneault, which is used on volunteers with all kind of new technologies that by ensuring that it's always safe for the patient. So on the left, on SAM, you can see with the white arrows on the reference case, the oils that are created during measurement. And for SiC, barium titanate and calcium titanate, you can see when using those pads, those all are partially or fully replenished. And most of the time, it's not that much in terms of field compared to the field at the center of the head, but that field that you are added is enough for having a good image in those spots. When you are on volunteers, you can see in white rectangle, the temporal lobes holes. You could see that when using the pad, those holes are filled. And also there is something very common that you could have seen also on the paper of Schmidt I showed you for silicon carbide and barium titanate. You could see there is a hole that is created while the field is replenished. In the case of calcium titanate, you don't have that effect, because the permittivity is 3 times lower. So you have just the field that is, the field that is much higher. And when we made some kind of conductivity measurement, you could see that the field increase in those area are at least equal to 25%. We would expect that the silicon carbide is a bit lower than barium titanate, because the conductivity is higher. So here I show you that we have on the right side the brain images corresponding to the B1 plus map on one volunteer we had. We did it on 5 volunteers. So the values you see here on that slide, they are computed on 5 volunteers. So on brain image, you could see that we have a better intensity in the temporal lobe for all the pad, even though the increase is lower. And also, as you told you, we were using barium titanate pads that were more than 6 months old. So you can see here, the solvent started to evaporate. And also there is a formation of water. We assume there is formation of water on in the pads. That is not heavy water anymore, but pure water. And you're starting to see the pad on the image. The image is still exploitable, but you know, with the pads, you have to acquire a larger FOV to have the same image if the pads are not seen. So you will lose time most of the time, and that's why when you are selling pads after 5 or 6 months, let's say 7 months, people are calling back to have new ones because they are starting to see the pads on the image. So we are trying to demonstrate that the pad we are using, they have the same performance as the pad used in the, by Andrew Webb and this group. And even if we use a dispersant, we have okay overall conductivity, and which leads to a bit lower increased field, but you still see the temporal lobe very well on the brain image. They are safe to use. SAR level and no are the cell level of magnitude as perovskite pads, and on top of that, it's not, you know, it's not harmless, it's not harmful, sorry, as the perovskite pads. Also, it is MR invisible for a longer period of time. Sorry, I've typed it's a longer period of time. It's something that I explain with the fact that it is a pasty material compared to barium titanate, which is very liquid. You can see it when you do it. When you put it in the bags, and we are starting to seal the pads, it is very liquid. So yeah, there is no doubt that the liquid tends to evaporate at some time. And we don't have that much data, but we are starting to have them now to say that it remains pasty and comfortable over time. To finish that, we are presenting a poster with a bit more result on this. If you want to see it at ESMRM, we are adding on this simulation mostly on Gustav with B1 plus maps. So you are free to look at it, and I can give you a feedback or some kind of answers if you have additional question on those images. And to finish, I would like to say that there were a lot of contribution about this because it took a long time to develop. It was mostly an idea of Institut Fresnel. Then there was two postdocs in CEA to develop the new material. Because it may seem simple to take barium titanate in heavy water, but assembling the right kind of materials with same level of water, non-magnetic, is really hard. So there was a postdoc of 2 years before MCube to work on this. And after that, we worked during WorkCube to MCube to finish the project and have a material that is very close to CE marking now. So thank you for your attention, and if you have questions, I would be happy to answer them.
Okay, thank you, Zo. Do you have questions? I don't see any raised hands or anything at the moment. I had a couple of them myself. First one would be simple, I guess. I think you showed that there is, well, the pads that you use, they are just squares. Do you think if you can get some improvement by modifying the shape of the pads, so maybe conforming them to human anatomy or something?
I think there can be done a lot of studies, like the group of Wade, you know, on the shape of them. And also making an assembly can be helpful. As you can see on this slide, you see here there is a hole created. And for example, Rita Schmid with just assembly, she also had a hole here. But when she made an assembly of pad, the hole disappeared, and I think the overall homogeneity is higher. So yes, there is a lot of, I mean, there could be the work to be done on the shape, but the thing is, since my company is aiming at selling it, the simpler way of doing it is doing square so far. So we are doing only squares. Mostly,
yeah.
there is also a fact that when you are doing those, they are vacuumed, vacuum for a few minutes. So yeah, it will be hard to make a vacuum phase of the air in the composite before selling if the shape is complicated.
Okay. And another thing, maybe in following. Yeah, I think we have a question from Pavel. I will ask my attempt.
Oh, thank you for your presentation. I have one question, and in conclusion, you told that with pads remain best and comfortable. And during presentation, you compared the different type of pads, and in the beginning, you show that the main feature of pads it must be comfortable for patient. And can you explain some have you some estimation of the weight of your pads, and pads if it compare with different materials, it will be heavier or no? What about the weight of these pads? It's really comfortable for patient.
Yeah, you are right about this. I had some issue to prove how comfortable it is, because it's depends on the feeling of the one who is using it. You're totally right about that. And yeah, it's a difficult question actually. What I can say is that for the pad 18 by 18, with calcium titanate, when I saw the use on the patient during the measurement on restricted mode in neurospin, yeah, they are not comfortable. And one of the patient end up with a bit of skin lesion, because the pads are so big that they are folded at the back on his head, and he was spending 1 hour on them, and he had some skin lesion on. It was not harmful. It was harmless, but it has to be noted. It was not comfortable for him. So it was the best example I had so far. The second one is that I see it when I prepare them that it's less liquid and more pasty than perovskite pads. But you're right. So far, it's very hard to define really how it is comfortable for everyone else. I mean, different than me. So far, what I can tell you is that we are planning to make some kind of survey to all people that got calcium titanate and barium titanate pad. We had sell a few of them. We have sold a few of them, and we asked them to rate how comfortable they found it. But so far, yeah, it's a bit hard to define really, to quantify that part. And to finish, actually, on those measures, it was based on let's say a paper by Luisa Neves, where the barium titanate were machine pressed to have high conductivity, high permittivity. Actually, all the measures you see here are machine pressed, meaning that you take a press and with the pad below it. You press it until you have extract a lot of air, as much air as possible. And in the paper, you could see that you need, to have a solid recipient that can be machine pressed. And that was the last paper I had on barium titanate with such high permittivity. That's why they said that those ones were very rigid, because when we measured those at neurospin, yeah, it was really hard to put it just be on the side of SAM, because of they can be folded and they were very, very thick. But yeah, that's a very interesting question. I don't have that much answer apart those examples.
Okay, thank you. I had another question which came up when you were speaking about selling those pads to different sites. And I was actually wondering, so the thickness and the size of the pad, is it somehow related to the coil that you use to excite the field, and how do you deal with that? Because different people probably have different coils, and can you use the same pad with different excitation coils? And actually, can you use it, and will it be of any use in parallel transmit systems?
Actually, we just made simulation with a coil that resonate at the same frequency as 70 coil. But what we have done during the 2 years, I wasn't there for the 2 years postdoc. I was there only for the second year. And during the second year, we made a lot of simulation to have the perfect, I don't like the word perfect, but the best size for almost everyone. And then we tested it, and I think the results are in a poster we presented 1 or 2 years ago at ESMRM, where we ended up saying that that size is the best, give the best performance for us. But no, we just made some simulation on with a genetic 70 coil, and that's all. We claim that it can be used with all the coils on the market, but yeah, in fact, we don't know it, and that way we send it to the first pad was sent as as a sample, so they could test it. And after that, people come back to us with requirements for using it on patient. And after that, they have the result on their own coil.
Okay, what about the parallel transmit? Because I remember Georgi here recently showed a very fancy parallel transmit coil, which provided quite nice excitation profile. But do you think it can be further? Well, do you think the parallel transmit can be further improved with the pads, or it doesn't improve it anymore?
I think that it can be improved, but in itself, I am convinced that parallel transmission it's much beyond the pad. But on our side, at not at Neurospin, but at CRMBM, we have Tanya. I don't know if you have seen her work, but she did the same mostly, but at 3T. Meaning that she used pads in conjunction with parallel transmission, and yeah, from some kind of position, she had better images. I don't know if it can be, and I'm not familiar with how hard is it to manipulate the the parallel transmission thing, but I think it can be enhanced, but I can't say how much what are the limit of using pads and parallel transmission. But I think yeah, it's worth the time to work a bit on it to see how far it can be driven, of course.
Okay, thank you. So, are there any more questions? Okay, I don't see any. So, thank you, Zo, for your presentation. It was
Thank you for the opportunity. And I mean, if you want some pads, I mean, I wouldn't say that of the books, but from M-Cube. I mean, you could ask Reda, and he will ask me to send you some. We will, yeah, it will be. I don't know if you had them already, but yeah, I will be happy to send them to you from you know, on the M-Cube network.
okay, that's great to know. I think we have a couple actually that Alona made. So thank you, Zo. We are now moving on to the second part of a seminar where we would have a small presentation by Andrei Sayansky about some ongoing matters in the crystal, some procurement. So I think, Andrei, do you need the screen? And I think we will be switching to Russian for that part of the talk, as far as I know.
I'm afraid I'm not friendly, so I will be off
Yeah,
then.
okay, great.
Thank you very much, all of you, for your attention. So goodbye.
Yeah, bye. Bye.